Today we're looking at lesson 6.6, Symmetries of Quadrilaterals. And today's objective is, given a quadrilateral, I can list its symmetries, both rotational and reflectional, in 2 out of 2 problems. So there's some big words in there. Some of them might be unfamiliar, or some of them may be familiar but not sure how we'd use them in geometry exactly. We're going to get into that today. But to start off with, let's look at some vocabulary. So here's some terms that we've used so far in this unit. Can you remember what a right angle is? A right angle is a special angle that is measured 90 degrees. It's a 90-degree angle. How about parallel? Do you remember what the word parallel means? You might remember that it is 2 lines that never intersect. Or you might also remember it has something to do with slope. What slope did parallel lines have? Parallel lines have the same slope, but different y-intercepts. Okay, how about perpendicular? What did the word perpendicular mean? This was another word that relates 2 lines to each other. Well, perpendicular kind of combines 2 lines and right angle, 2 lines that meet at a right angle, that intersect at a right angle. Remember, we had a way of writing parallel lines that was like this, these 2 pipes. So we might write like line AB is parallel to line CD. And we had this other symbol for perpendicular, where we might write line EF is perpendicular to line GH. We also had a slopes definition of perpendicular. We said that the slopes are opposite reciprocals. Opposite reciprocals. And that was a fancy way of saying negative and upside down, flipped upside down for a fraction. Okay, good memory. We've looked at right angles, parallel lines, and perpendicular lines in this unit. Now we have some more vocabulary words that may look familiar. You may have seen these before in previous math classes, or you may not have, and that's okay too. What about a polygon? Have you ever heard of a polygon before? We can take this word apart. We can split it apart right there and take the prefix and sort of the suffix and figure out what those terms mean individually. So like poly means many, and gon refers to a shape. So this is a many-sided shape. But we have some specific definitions in geometry that we use to define polygons. One necessary condition is that it has straight sides. So circles are not considered polygons. They have to have straight sides. So the lowest number of straight sides you could have for a closed polygon is 3, which is called a triangle. And closed is actually our second criteria here. Closed means that if we draw straight lines, we can, they don't have to be regular polygons, but no matter how many lines we draw, eventually they're going to meet again. And they're not going to cross over each other. So this is our geometric official definition, at least as far as this class is concerned, for a polygon. It has straight sides, at least 3 straight sides, and it is closed. Okay, how about a diagonal? And here we're talking about diagonal as a noun, as in a diagonal, rather than describing something as like a diagonal line. What is a diagonal? So when we have a polygon, let's draw one up here. This is like a pentagon. We can draw lines from one vertex or corner to another. Each corner is called a vertex. And these lines that connect the vertices are called diagonals. Notice that I'm not drawing the lines on one vertex after another because those are already sides. Those already exist. So those aren't separate diagonals. Diagonals only go between corners or vertices that are not right after each other. So the way we write that is a line that connects two non-adjacent, that means not right next to each other, non-adjacent vertices. Vertices was another name for corners of a polygon. So that's our very formal definition of a diagonal. It's a line that connects two of these corners in a polygon. Okay, how about quadrilateral? That's another one we can pick apart, cut in half like that. What does quadra mean and what does lateral mean? Quadra, or you might recognize the shorter prefix, which is quad, that means 4. And lateral means side. So if you think of like lateral bends or your lats, which are a muscle group that help you bend from side to side, quadrilateral means 4 sides. So this is a 4-sided polygon. And you're probably familiar with at least a few of these. Some examples are squares, rectangles. You may have heard of a parallelogram, or maybe a trapezoid, or a rhombus. All of these are examples of quadrilaterals. If you haven't heard of some of those, don't worry too much about it. We're going to get into them in just a minute. Our last term on this page is congruent. Have you heard this term before? What does congruent mean? We have kind of a hint underneath it. It asks, do congruent and equal mean the same thing? So that kind of leads us to believe they must at least mean similar things, right? So congruent means two shapes are the same size and the same shape. So two objects in geometry. So we could be talking about a line, we could be talking about a triangle, we could be talking about an octagon, we could even be talking about a circle. But they're the same size and the same shape. They could be in different places, they could be reflected. Remember, we've been talking about rigid transformations, right? That produces an object that is the same size and the same shape, but it might be in a different orientation or it might be somewhere else on the plane. So another way to think about congruent, now that we've been talking so much about rigid transformations, is we could also think of it as the result of a rigid transformation. Or more, one or more. Or more. So a rigid transformation will produce two congruent shapes. So this question, do congruent and equal mean the same thing? We'd be asking, are these two shapes equal? Well, we typically in math, when we're being very precise, congruent is a geometry term. It refers to shapes on the plane. And equal is a term that we give to numbers. And numbers are not exactly on the plane. They are measures on the plane, but they aren't themselves shapes. So when we're referring to two shapes being the same size and shape, we would call it congruent. Or if we're talking about numbers now, if we're talking about 3, like x equals 3, we would call that equal, not congruent. And it gets a little bit tricky when we talk about line segments. Like if I wrote a line segment right here, and call this line segment AB, we could have another line segment over here that's the same length, called CD, and we would say that AB is congruent to CD. Line AB is congruent to line CD because they're the same length. We just moved it, probably rotated a little bit in the plane. This is different than the length of AB, which we'd write like this. The length of AB is equal to the length of CD. It's a very nuanced difference. Notice we use a different symbol. This is the congruent symbol. This is the equal symbol. The length of AB is some number. We could say this is length 2. This is also length 2. So this is essentially saying 2 equals 2. Those are numbers. But these are objects. These lines are congruent because their lengths are equal. All right, so let's get into quadrilaterals. That's what we're looking at in this particular lesson. We are going to talk about symmetries of quadrilaterals. So let's talk about what those quadrilaterals are. We mentioned these a moment ago: rectangles, parallelograms, a rhombus, a square, and a trapezoid. So we've been looking at rectangles probably since we were about 2 years old. We've been naming it since then. But we need a precise definition of what a rectangle is. What features does a rectangle have, or do all rectangles have? We know that they all have 4 sides. We know that they all have 2 pairs of parallel sides. We know that they have 2 pairs. We know that they have 2 pairs of sides that are the same length. Remember, we just learned that fancy vocab term we can use now, congruent sides. And, let me show you little bullet points. And we also know that they have 4 right angles, right? So a rectangle looks something like this, where all of these angles are right angles. These 2 sides are the same length, and these 2 sides are the same length. Okay, so what's a parallelogram? We've got the definition here: 2 pairs of parallel sides. Do you know what a parallelogram looks like? It looks something like that. Notice this also has 4 sides. Now you may notice we said that a rectangle has 2 pairs of parallel sides also. These both have 2 pairs of parallel sides. So actually a rectangle is a special kind of parallelogram. It's just a kind of parallelogram that we sort of shifted this way until these formed right angles. All right, how about a rhombus? Here's a picture of a rhombus. Looks like a diamond maybe, or a squished square. We notice this also has 4 sides. That will in fact be a feature of all of these because these are all quadrilaterals. So a rhombus has 4 sides. What else do we know about rhombuses? Have you ever seen these before? So rhombuses have the same length on each side. All of those sides are the same length. But these angles obviously are not the same because these ones look acute and these ones look obtuse. So they don't have the same angles, but they have 4 congruent sides. Okay, now we have a square. We have a picture of a square. What do we know about squares? We know that squares have 4 sides, like all of these. They have, their sides are all the same length. So 4 congruent sides, using our fancy vocab term. And we also know that they have 4 right angles. So all of these sides are the same length, and all of these angles are 90-degree right angles. All right, so our last one on this page, trapezoid. What is a trapezoid? Well, a trapezoid is a little bit different than all these other ones we've been talking about. All of these so far have 2 pairs of parallel sides, so they all qualify as parallelograms, but this one doesn't. This one has exactly 1 pair of parallel sides, so it looks more like this. And you can have different types of trapezoids. You may have one that looks like this, but the other side goes way out like that. That is also a trapezoid. If these 2 sides are the same, we call it an isosceles trapezoid. And if they're not the same, we call it scalene. You may recognize those words because those describe triangles as well. Same idea. 2 sides that are the same are isosceles. These 2 sides are different. That's a scalene trapezoid. Now you may also have noticed that a rectangle and a square sound very similar. They have a lot of things in common. They both have 4 sides. They both have 2 pairs of parallel sides. They actually both have 2 pairs of congruent sides. The square just happens to have them all be congruent. And they both have 4 right angles. And that's because a square is actually a rectangle, but it doesn't go the other way around. A rectangle is not necessarily a square. It turns out these can be arranged in a hierarchy that looks like this. We start with a quadrilateral on top, polygons with 4 sides, and we divide those into trapezoids and parallelograms. On the one side we have trapezoid that has exactly 1 pair of parallel lines, and on the other side we have parallelogram, which has 2 pairs of parallel lines. So this is divided by the number of parallel lines. You might think to yourself, well, we should have another one, right? We should have one that doesn't have any parallel lines. Something maybe that looks like that. None of those lines are parallel. And that does in fact exist. We're just not going to worry about it too much in this class. This is a valid quadrilateral. So over here we have a parallelogram that further divides into a rhombus and a rectangle. A rhombus has 4 congruent sides, and a rectangle has 4 right angles. We could also call that 4 congruent angles. They are the same measure. They are angles that would be exactly the same if you were to rigidly transform them onto each other. But rhombuses and rectangles both qualify as parallelograms, and all of these qualify as quadrilaterals. So then below that, we have a square. A square is an instance of a rhombus that is also a rectangle. It has 4 congruent sides and 4 congruent angles that happen to be right angles because it's a quadrilateral. A square is also a parallelogram, and a square is also a quadrilateral. This is a really good page for your notes if you want to take a screenshot of this. All right, what does symmetry mean to you? Think about that for a second. What is symmetry? How would you describe it? Or if you were to draw it, what would it look like? What does symmetry mean? we often think about it as something that reflects the same on both sides of a line. Right? We think of it like a mirror image. Or maybe like this shape is a familiar one. Sometimes, maybe when we were little, or even now, we've folded pieces of paper and cut them up into snowflakes. That line made a line of reflection, so snowflakes maybe look like that, or we cut diamonds out of them, something like that, and then we'd have a round snowflake. So that would be a case of symmetry as well. What do we have? Some triangles over here, some triangles over here, like that. So we have a more formal definition in geometry, one we take out of a textbook. And a symmetry is a transformation that produces the exact same object. So this is a congruence. We do have congruent shapes here, but we have an additional feature where our transformation produced the same size, the same shape, but also in the same location. So it's like you did the transformation and it landed right on top of itself. That's what we mean by symmetry. We did one of these rigid transformations we've been talking about. A translation, a reflection, and a rotation are the three we've looked at. If you do one of those and it lands exactly on top of itself, exactly the way it was before, we call it a symmetry. And we're going to look at two different kinds based on those transformations we've been talking about: reflectional symmetry and rotational symmetry. We tend to think of reflectional symmetry first because that's just what comes to mind, mirror images. But rotational symmetry, you can see, you can rotate like this flower up here or this starfish. If you rotated it, you'd have it land on itself several times until it got all the way back around, and then it would land on itself again. So let's take a look at these a little bit more closely. Reflectional symmetry says that a line of symmetry exists that maps the object onto itself. And we're supposed to draw a line of symmetry for each of these images down below. So you'll notice symmetry happens a lot in nature. So that's why we have pictures of nature down here. So we have this bird. A line of symmetry would go straight down the middle of that bird. And you can see if we were to reflect that bird across the axis, that wing would end up right on top of that wing. That half of the tail would end up right on the other half of the tail. Similar with this elephant, we could draw a straight line down the center, or approximately down the center. And the elephant's ear would match up with that ear. So you'd reflect it across and it would land there, and this ear would land over there. So the elephant in its entirety is considered symmetrical over that vertical line. We have a pea pod here, and on this one we could draw a horizontal line of reflection. If we reflected this up and this down, they would land on top of each other. Now this one's just approximate, right? They all are a little bit approximate. We have little deviations in nature, like this bit over here, but these are approximate symmetries. And how about this butterfly? We could draw a line of reflection, well, pretty close, kind of diagonal down this way. Notice that diagonal lines can be line of reflections. They don't have to be vertical, they don't have to be horizontal, they can be diagonal as well. They can be any direction. So let's take this over to a polygon. How many lines of symmetry does this square have? Can you draw some? Where could we fold this square and have it line up with itself? Let's see. I think we could fold it in half that way. And we could also fold it in half that way. Oh, kind of put it closer to the center there. And we could also maybe fold it that way into triangles. And this way. So how many lines is that? This is one line, two lines, 3 lines, and 4 lines. We've already got this one labeled 1, this one labeled 2, this one labeled 3, labeled 4. So this is 4 lines of symmetry. And if we want to list them, we'd have to describe them, right? So we'd say both diagonals are, because we've got this diagonal and this diagonal. And then we have these other 2 lines. We have a vertical line and a horizontal line. There's the vertical line, there's the horizontal line. But we need to be careful here. We need to specify which vertical line and which horizontal line, because this is another vertical line, right? But this one is not a line of reflection. We can't reflect this over and have it match that one. Similarly, this is a horizontal line, but it also is not a line of reflection. This side doesn't match that side. So how do we specify which vertical line this is and which horizontal line this is? Well, we know it's a line of reflection because both sides are the same length. So that means this must cross at the middle of both of these sides. And we had a fancy name for that, actually. We had a fancy name for intersecting in the middle, and that was a bisector. Vertical bisector of opposite sides. Fancy term, right? But bisector, remember we took that apart. Bi just means 2. Sect means to cut. So cut something into 2 even pieces. This is the vertical line that cuts the sides into 2 even pieces. Similarly, this is the horizontal line that cuts the opposite sides into 2 even pieces. So this is the horizontal bisector. Bisector of opposite sides. Now, is that true? Do all squares have 4 lines of symmetry? Or is that only true for this square we're looking at? What do you think? Would all squares' diagonals be lines of symmetry? And would all squares' vertical and horizontal bisectors be lines of symmetry? What do you think? This is true for all squares, because a square could be dilated, right? You could make a square bigger, you could make it smaller, and all of these features would still apply. You'd still have these diagonals. They'd still cut it in half. These ones would still cut it in half. So all squares have exactly 4 lines of symmetry. All right, so I think we have a good handle on reflectional symmetry. Let's talk about rotational symmetry. And our definition of rotational symmetry, it's not quite as intuitive, we don't jump to it right away, is there's at least one non-trivial, we'll talk about what that means, one non-trivial rotation angle and center of rotation that maps the object onto itself. So you can think about spinning this around, something like a globe spins around itself. What do we mean by non-trivial though? Well, if you look at any of these objects down here, any of these pictures, if you were to rotate this all the way around until the top side was here again, of course that would land on itself, right? You rotated it all the way around. So what we mean by non-trivial is not 360 degrees, because everything has rotational symmetry at 360 degrees. And if everything has rotational symmetry at 360 degrees, it's not a very useful or interesting thing to say, right? It's just a universal property of geometry that everything lands on itself when you rotate it 360 degrees. So if we want to talk about non-trivial symmetries, we're going to talk about symmetries that are less than 360, something that is under a full rotation. So let's look at least one of these pictures down here. Let's look at this little sunflower looking flower. What degree do you think you could rotate this, or what fraction of a circle could you rotate this to get it to land on itself? Well, what if we divided this into quadrants like so? There. If I rotated this 90 degrees down, this petal would kind of land right on that petal. This one would land here, this one would land here. That looks like 90 degrees would be a good rotational symmetry. Notice if we rotated it 180 degrees all the way down here, the same thing would happen. 180 degrees is another rotational symmetry. Same with 270. Since all of these quadrants appear to be what we would call congruent, any 90-degree rotation around will also produce the same image. So these are all rotational symmetries of this flower. There are actually more, because even if we only went this far, right? If we only went from here to here, whoops, from here to this petal, if we only did that distance, that angle right there, much smaller, we would still get a rotational symmetry. Each petal would rotate onto the next one. Same with this angle right here. That is another rotational symmetry. So this flower has many rotational symmetries, but really obvious ones are 90, 180, and 270. Now you can take a look at this succulent here, kind of a aloe vera type plant. We're not going to look at that one too closely because it's a little bit complicated, but you can sort of view, if you were to rotate it, it would, at some point, this little piece right here would land on that piece. So we'd be asking, what is that angle right there? Or maybe this piece would land on this piece, and then we'd be looking at that angle right there. It's kind of hard to see in blue on green. Maybe I could get a different color here. Maybe pink? Would pink be better? There you go. What's that angle? Similarly, with this snowflake, what do you think? What would be a good angle to rotate it here? You might try 90 degrees. 90 degrees is one of our common ones. But if we rotate it 90 degrees, notice this absence of arm here would rotate onto this arm. So this space would now be an arm. 90 degrees doesn't work as a symmetry on this one. But if we rotate it all the way around to 180 degrees, so that the top becomes the bottom, notice this one will move over here, this one will move here, and this one will become here. So this one has a rotational symmetry of 180 degrees. So, applying this to polygons again, what are the rotational angles of symmetry for a square? What can we rotate a square to get it to land on itself? Well, we know that all of these angles are congruent to all the other angles. So if we move this angle down here to this angle, what's that rotation? Or another way to think about this is if we drew quadrants right over the top of it. This looks like the quadrants on the graph now, right? This is Q1, this is Q2, this is Q3, and this is Q4. If we rotated quadrant 1 this way, it's effectively the same, right? It's the same size and same shape as quadrant 4. So that's a 90-degree rotation. This is a 90-degree rotation. This is a 90-degree rotation. And anywhere in between those, this corner would end up here at a 90 degree, but anywhere in between those, this corner would be poking up, right? It would be poking up somewhere on the side. So really, there's only 1, 2, 3 places, and then back to itself, that we could get that corner to line up. So 90 degrees, 180 degrees, and 270 degrees are our rotational symmetries for a square. And once again, we're asking, is that true for all squares or just this one? Well, all squares look pretty much exactly like this, scale up or scale down. Right? They all have the same length of sides, same 90-degree angles. They just get smaller or bigger. So this is true for all squares. All the rotational angles of symmetry are 90, 180, and 270 for all squares. All right, that wraps up what we're going to look at today, how we're going to introduce symmetries of quadrilaterals. We'll be expanding on this tomorrow with other kinds of quadrilaterals. Given a quadrilateral, I can list its symmetries, both rotational and reflectional, in 2 out of 2 problems. So we looked at squares today. We'll be looking at other quadrilaterals tomorrow.